Okay, let's start. A student will come and then join.
Okay.
So, this week, one content we will discuss some problem related to the degree of freedom, some problem related to the equivalent stiffness of the system, and some problem related to the governing differential equation of the motion. So that and everyone, can you hear me? Am I audible? Am I audible?
Yes, sir. It is audible, sir.
Okay, okay. So, like this week, we discussed three type of problem. One is the degree of freedom. One is the equivalent stiffness of the system, and the two problems are related to the like the how we generate the how we develop the differential equation to find the solution. Like the solution will come in the upcoming sessions. In this week, we generate only the differential equation. Okay. So first, let me share my screen. Is it visible to everyone?
Yes, sir. It is visible.
Okay, let me like unpin this one. Wait. Okay, let's start. So this is the course of dynamic of structure. Like the course instructor is the Professor Manish Kumar, and I am the TA for that same course. So we will discuss the sixth problem in this session. So the first problem is related to the determine the degree of freedom of the system. So, like, can you tell me, like, in the chat box, you can write, or you can, like, say, or like, unmute yourself and say, like, what is the degree of freedom of this system? One, two, three, four. Anyone? Oh, someone gives the answer two. Anyone? How it can be two? Anyone? Like, you can think little bit about like how it can be two. Like, if you are thinking there is a number of strings two, then the degree of freedom two. Let me tell you, like, first, like, if you can do the deflected shape of the system, then you would be able to like find out the degree of freedom of the system. So let me show you the deflected shape of the system. Now anyone can tell me, like, what is the degree of freedom system by like seeing this deflected shape of the free body diagram system of the anyone. Okay, in the chat box I have can see that the one, because if we give the theta rotation in the clockwise direction, so the deflection in the spring, both the spring can be the deformation in the like the terms of the ratio, like in the terms of the theta, we can express the deformation in the like the spring one, like the like in the spring says, like, let me use my pen. So like the this in this spring and then is in both the springs, the deflection would be the some theta time like L by 2 or some any length of the, like that can be L by 3, L by 4, whatever, but the that system can express in only one coordinate system. Like so, the degree of freedom of the system is 1. So I have written the statement is also, like if the theta is the angular rotation of the bar in the clockwise direction, then the due to the rotation of the bar, displacement in both the spring can represent in terms of the theta, as we have written here, and this will also the theta time L by 2. Okay, now come to the next question that is related to the, like equivalent stiffness of the system, like this system. So this kind of question may be in your also the upcoming week one assignment. So, like in this question generally, many time you can ask like why this question is not a multi degree of freedom system, because this is a beam also has some mass, and the cantilever beam has also some mass. But in this system we are considering that the both the cantilever beam and the simply supported beam both has massless. Okay, massless. So, like can anyone tell me like how we combine these systems? Like first, can you can calculate the uh, stiffness of the cantilever beam? Like can anyone tell me what is the stiffness of the cantilever beam? Like only formula, then calculation you can do easily. You can write in the chat box, or you can like give some unmute yourself and can tell me like what is the stiffness of the cantilever beam, directly formula.
PL cube by 3I.
So P, where if the P is not here, that would be only the 3I by L cube. Because for the stiffness, how we determine, like the unit load. If we apply a unit load, then what is the deflection? So for corresponding to that unit load, what is the stiffness? 3I by L cube. And same for
Okay.
the simply supported beam. Anyone can tell me? Like due to unit load, or if you apply a P load in the, like the middle of the beam, what is the deflection? That will be around some PL cube over 48 EI. Okay, so what is the stiffness? Stiffness would be the 48 EI by L cube. Okay, so first I have calculated the stiffness of the cantilever beam, EI by L cube. Like the values of the E and I are given. Like this is the same for both the cantilever beam as well as the simply supported beam. And same we have calculated the stiffness of the simply supported beam, that is the 48 EI by L cube, that comes out to be 3935232 Newton per meter. Is there any doubt here up to this? Okay, then we will like, now we can consider it is a system, like stiffness springs, like we can consider beam as a spring here also. So like I will show you a free body diagram in which you can check like what is the how these springs are combined. Okay, so we have to combine, like the degree of freedom of the system is given in the x direction, only this x direction. Like we have to combine with respect to this block, mass block. Like we have to combine this system, all this system, and then this spring. Then we can tell like what is the effective stiffness. Like some system will become like this, k equivalent, and some mass block, and the displacement is in x direction. Okay, so first let I define like the first spring as the spring 1 in the top of above the simply supported beam, and the spring 2 above the mass block, and the bottom one is the spring 3. So can you tell me, like spring 1 and the cantilever beam, like if this cantilever beam we can like if we remove the cantilever beam and if we make a spring like this, like, or you can if we apply any load at that point, like if we apply any load at that point, so the deflection would be like some deflection in the first there is deflection in the then in this cantilever, and then the spring. So these two springs are in the series combination, like the deflection is different in both the springs. Okay, so for the series combination, how we calculate the stiffness? 1 over k equivalent is equal to 1 over k1 plus 1 over k2. So k1 you can write it as a the spring 1, and k2 you can take as a cantilever beam. Like these two springs would be in the series. Okay, then after this k equivalent calculation, if we remove this part, and this system whole system can represent as a spring, like this spring, which is stiffness is the k equivalent. Now we have the like the some simply supported beam, and we have a spring here, and if we apply a load like deflection at that point, like that, so the deflection on the in the both the springs and the beam would be same, because like how much is the deflection in that, due to the compatibility condition or some, like if you look at the geometry, if you apply the deflection, like the both the springs and the cantilever will be the same. So if the deflection is same, then the series combination springs are in the combination of the parallel. Like if you have like the studied, like if the displacement at the points are different, then the series is the combination is in the series. And if the deflection is in the like the same at the points, like these two springs, like there, and the these are the this is the some mass block. If I give the some displacement x, so displacement in both the springs are same, so these two springs are behave with the parallel. So I will calculate the upper spring. Here is the upper spring is this k equivalent one. Okay, upper spring this one. Okay, and the simply supported beam, both springs are in the parallel. So for the parallel combination, what is the stiffness of the system? Kb plus k equivalent 1. Okay, so you can calculate the k equivalent 2. Now after calculation this, we can remove the also simply supported beam. Like we can how we can represent this system? Like this whole system is gone. Now this system become this, like spring, then joint, then spring, which is k equivalent. Like this system also, like a whole is the k equivalent, sorry, like this whole system is the k equivalent 2. Okay, and then another spring which is spring 2, k2, and then a mass block, and then a spring. So now this become a simplified problem. Like these k equivalent and spring 2 are in which combination, can anyone tell me? Like
Series combination.
series combination. So now you can directly, like the like what is the series combination, how we can, like just the shown in the upper, like the first k equivalent one. So the k equivalent 3, like we give this name as a k equivalent 3. So this become as a 1 by k equivalent 2 plus 1 by k2. If you add and do the calculation, you will get the stiffness of the k equivalent 3. Now after the removing like this spring, that this is become the k equivalent 3. Now this spring and the niche, like the bottom one spring 3, in which combination?
Parallel combination.
Okay, so this is the parallel combination. So you can directly add these both the springs k equivalent 3 and k3, then you will get the total stiffness of the system, which would be the 1.39 into 10 raised to power 5 Newton per meter.
Excuse me, sir. The
Yes.
series and parallel, can you clarify once again? There's some confusion. When you say
Like
consider parallel.
series combination is where the displacement is different,
Okay.
and the parallel combination is where the displacement is same. If the displacement is same, like let us draw some, like this one spring, then another spring k1, k2, and I apply a force. So like these stiffness, like the total force in the spring, like transfer by this spring and this spring would be same, but the displacement in both the springs are different because the stiffness is different. So the total force is the F is equal to F1 plus F2, and the that will be the K1 X1 plus, sorry, the displacement. Here we take the displacement as equal. Like we write it as a, like the total displacement is if X, so the displacement in the first spring is the X1 and the displacement in the second spring is the X2. So how can I write X? X can be represented as a F by K. Okay, and X1 is the F1 by K1 and F2 by K2. So in this, the force transfer by the springs, both the springs are the same. So that will be cancel out. Like F1, F is equal to F1 is equal to F2. So my spring series, in series combination, my K equivalent will become as a 1 by K1 plus 1 by K2. Understood or any doubt?
This is in actually series then,
Yes, yes, this is in the series combination.
but it's not with respect to
What?
that series or parallel should be seen with only with respect to deflection, not with respect to geometry.
Yeah, now we have to check the deflection, not like geometry. How can you like define like the with the looking the geometry? You have to look at what is the deflection at that point.
Okay.
Okay, then same kind of problem is the, like we are taking two, like the, if you have some confusion, like same kind of problem is the next problem, so that you can try this combination. This is the some easier problem. You can try yourself. Like you have, like you haven't given the value of E and I. These are the in terms of the cantilever stiffnesses you can consider as a Kc, and the stiffness of the both the springs are same K and K. So first you can try like the what is the upper combination. Like if you remove this spring, like let us, we have the system, this cantilever beam and then a spring only, and we apply a force F, then you can think about like what is the displacement at that point. If you think like if the displacement is same at the both the point is the in the both the spring and cantilever or the different, can anyone tell me? Like if I apply a force in this cantilever beam here, and there is a spring and that is the cantilever beam, so the displacement in that point, like the spring and the cantilever is same or different?
Same.
Same. So if this is the same, then what is the combination? That would be the parallel combination. Okay, so first calculate, like we have calculated the stiffness of the cantilever beam, that is the 3I by L cube. Like the same kind of statement which I have draw here, like written here, the cantilever beam like as a linear spring, the displacement at the end of the upper spring and the end of the cantilever beam are the same, like the displacement is the same, thus the beam is parallel with the upper spring. After that, like we have like the these are in the parallel combination, so that K equivalent 1 become as a 3I by L cube plus K1. So now you have one spring and then another spring and then the mass, then this, what is the combination of this? Anyone?
Series combination.
Okay, series combination. So then directly you can add these systems. Like for the series combination, like your 1 by K equivalent is equal to 1 by K equivalent 1 1 plus 1 by K2. Okay, so your, like if you put the value of the K equivalent 1 and the K2, you will get the overall expression for this one. The same kind of problems maybe has given in your week 1 assignment for the calculation of the springs, like the equivalent stiffness, not much differ. Like again we have one more question that is very simple, like engineering mechanics type question. Like if you give the displacement in the x direction, or like we have to find the k equivalent, like only one mass here, that like we have this point, like give the displacement in the x direction. So you can tell me like what is the, like the combination, like if we give the displacement in the x direction, so deformation in the all the springs would be same. So that is the which combination? This is the parallel type combination. So can you calculate the stiffness, k equivalent stiffness of the system?
12 into 10 power 5 Newton per meter.
Okay, anyone has calculated?
12 into 10 power 5 Newton per meter.
Yes, yes, I hear your answer. Like some other student has calculated or not, I am waiting for them. Like let us consider force in the spring one is F1. Like you can consider any spring, like this consider one, this consider two, this consider as a three. And if we the force in the x direction is given, so like if we give that force or displacement in in this direction, so the resisting force in this up like the in the opposite direction, so that is then the x direction, that will be some theta. So that will be f, like in this type is this is the 2, so f2 cos 30, like this is the cosine component, cos 30 in that direction, that would be the f1 cos 45 degree, and that is the f3 cos 45. So this is the parallel combination. So if you add the, like in the x direction, if you add like total force in the x direction would be the f1 cos 45, f2 cos 30, and f3 cos 45. And if you put the value of the f1, like the you have the f1, what is the f1? F1 is the sum k into x. Okay, so that is the for the f1, this is for the f2, and this is for the f3. And if you do the further calculation, so I get this is the 9.12 into 10 raised to power 5. So my displacement is the 9, like the stiffness is the 912 kilonewton per meter. So what you get, the someone has given me the answer, like some 12 1.2 or some 12 into 10 raised to power 5. Anyone else, like is there any doubt in this question?
Sir, here it is not enough to directly add like K1 plus K2 plus K3.
No, here we are directly taken like the force. Like we have given the, like in this question previously, you like we have provided the forces in the fx direction. So the forces, like we are summing up the force in the fx direction and in the y direction. Like fx direction, what is the component in the x direction? F1 cos 45, F2 cos 4. Like you have to like look at this is a mechanics type problem, not like directly summing up the k equivalent k1 plus k2. Not like this problem is not like that. like like the forces in the like the some, like these springs are at some angle, so we have to like take the x component and the y component. So here we have not in the y direction, we have not like applied any force, so we are taking only in the fx direction, and then the component of the each spring in the x direction, that would be the some, like I have shown in the, like the this one. So if, and the displacement in the each spring would be same, because this is the parallel combination. So the forces you can like directly, like f1, you know, k1 x1 k1x plus f2 is the k2x plus f3 is the k3x. So you have the k1 k2 k3 values, and then you will get the, maybe you have directly added all these values, so you are getting the like 12 into 10 raised to power 5 newton per meter.
Okay, sir. Understood. Understood.
Okay, so now like we are moving to the generating the differential equation of the problem. So Now these are the equivalent stiffness questions. So you will be now able to solve these questions which are in the week 1. Maybe I hope so. Like maybe degree of freedom system, I have taken one example, but I hoping that you will be able to solve these like 2 or 3 questions which I have given in the week 1 assignment related to degree of freedom and the equivalent stiffness of the system. Now we are coming to the equation of the motion system. Like a system, a rigid mass beam is given to you, this one, and it is a pin up. Like this beam is pin at the point B, and a damper C is here, and the a spring of K is at the point D, and we are giving a displacement in VT direction, like the degree of freedom, like we are giving the deflection in this beam as a this. Okay, and there is a force also applied in this. So you have to develop the what is the equation of motion of that system. So first you can draw the what is the deflected shape and what are the forces are coming on that. Like if I have like rotate, I have provide VT, this kind of VT displacement, so that would be the theta. So can you tell me like what is the displacement at the point of D and what is the displacement at the point of C? First you can draw the free body diagram. Like if you are able to draw the free body diagram of any question, any system, then 50% work has done. Like you can, after the free body diagram, you can solve any problem. So like if I have given the displacement at point E is a vt that is given in the question, so let us the rotation theta at the point B. So this is like I have like the same problem, same figure, and the free body diagram is this. Like this point I have given the from here, that is the VT. So there is a some force, resisting force develop in the spring. Let us that force is the Fs. There is some resisting force develop in the damper, that is Fd. Okay, and there is some inertial force of the beam or the rigid rod, which is I theta double dash. So first we have to calculate what is the value of the Ft, what is the value of the Fs, what is the value of I, moment of inertia, mass inertia, like the inertial mass of the road. So first, if the Vt is the displacement at that point, so how much displacement at that point, at the D point? That would be simple. Like this is the, like the length is total length is the 3L by 4. So if I divide Vt by 3L by 4, this is my theta, and if I multiply this with the L by 2, that would gives me the displacement at the D point. If you get the theta, then you can directly get the displacement at the point D and at the point A. Okay, so the theta value is the Vt divided by 3L by 4. Now if we like we have rearranged the terms. Now with the same, we are getting the values of, like the displacement A is the theta into L by 4, which I have told earlier. Like this, like this is the point where the hinge, and at that point these are the L by 4, L by 4, L by 4, L by 4, and L by 4. So at that point, what is the, sorry, this is the point A, and this is point D. So at point D, that will comes out to be multiplied with the L by 2. Now we have to take the moment about the B, like the pin support. Anyone can try to take the moment about the B and can tell me the what is your equation coming out this. Have you understand up to this point, or you have any doubt up to this? Anyone? Anyone has any doubt? Am I audible?
Okay, sir.
Yes, sir, it is audible.
Okay, so is there any doubt up to this point, or I should I move further?
You can continue, sir.
Okay, so I have taken a moment about the B, which is the pin joint. So that will be the like, so there is some inertial force which I have like shown in the previous figure, I theta double dot, and that is in the clockwise direction, and there is some force Ft that was in the downward direction. Sorry, and there is a like F damper force in the upward direction and Fs in the downward direction, and there is some kind of load here in the upward direction. So the Fd damper force into L by 4, this moment about B, and this is the force moment, and that is the loading, that is the some P naught loading, and that is applied up to the distance of L by 2. So the total load will be the P naught into L by 2, and the moment of this load is the at the center of this. So the distance of this is the also the L by 2 is equal to 0. Okay. So now can anyone tell me what is the value of I? Like if you have this road, the length is L, about the center, what is the value of I? Anyone can tell me. What is the inertia of this road about the center? This is the simplest, like anyone, you can like, this is the like anyone has remember this, like you, if you have read it in the your class 11th or 12th also, standard 11 12, like about the center, that is the ml square by
ML
12.
square by 12.
Now we have to calculate, because we have taken the inertial force about moment about the point B. So you can take the moment about the, like we have to calculate the inertia about the point B, point B. So how can we calculate? Like parallel axis theorem generally we apply, like about this, like the inertia about the center plus mass into like the distance between these 2 points. And what is the distance between these 2 points is the L by 4. So that will the L
By
by 4 square. Okay, so that will be the 1 by 12 plus 1 by 16. If you will take some LCM or something calculation, you will get your I. Can anyone tell me what is your I? Anyone can tell me what is the value of I you have got?
7 by 48.
7 by 48 ml square. Okay. Anyone has calculated? Because these kind of, you have to do the calculation of your week one assignment to calculate the like the generate the equation of motion of the systems. Like there are 2 3 examples are related to like the inertial of the bar. Okay, so my I value is the 7 by 48 ml square. And anyone can tell me the what is the FD value and FS, because FD is C into like the what is over my displacement is that point A point, that is the VT by 3. So that would be the V double dot T by 3. And same for the Fs. If you calculate what is the displacement at the Fs point, at the point, this point D point, the displacement is the 2V by 3, and we multiply with this K, so that will come down to the spring force. Okay, so the FD and Fs are coming out to be C into V dot T divided by 3, and the Fs is K into 2VT divided by 3. Now we put this value in the equation, like these all two values are in this equation. You will get this equation. And you can rearrange this equation, like divide by L in the both the side, or some take the some common factor which will cancel out each other, and then there is a final equation, both side divided by L, and this is our final equation. Is there anyone has any doubt in this question? Anyone? Is there any doubt? Like if you are doing like calculation by yourself, then you can try by yourself also. Like these materials also will be shared with you, like the PowerPoint and the, as well as the like the video. But if you do it here like during this session, so that would be helpful. If you have any confusion during this solving the question, you can clarify this.
Sir, here the term P0 into f of t L by 2, that is the uh, deflection due to external load.
Yes, that is the like applied the load, like we are like there is a external load is applying.
Okay, okay.
Yes, that is moving in that direction. If like some questions, if there is, if you will get like there is no, like no this kind of, there is no p naught external load, then for the getting the free vibration terms, like this is the, you can consider this system as a force vibration type. Okay, like if there is a no force, then you have to consider like we are giving some displacement at that point, and like we are this is that that system would be the free vibration type. So here in this question you asked to like the generate the equation of motion, so we develop the equation of motion here in terms of vt. Sometime they will ask in the questions that can be asked to develop the equation in terms of the theta. So you have to replace Vt with the theta, like what is the relation of the theta and the Vt, so that you can calculate the in terms of the theta. Like any parameter that question can be asked. So these different type of questions has been asked in the like the like in the week one assignment. Okay. So any doubt or else, or I should continue?
Here Vt is to be considered the exciting force, or P naught is the exciting force.
No, yeah, P naught is the exciting force. Vt is the like we have considered that due to the excitation force P naught, there is some displacement at the Vt.
So it is only displacement.
Yeah,
Okay.
Vt is the displacement.
Okay.
Vt is the displacement here. Like this is the case of the force vibration type. Is there anyone has any question? Should I move or any doubt? Anyone? Anyone has any doubt? Okay, let us move the last and final question of this tutorial. This is the case where we have not given the like this is also the like the force is not given, like a rigid beam is given to you, the beam bc, and this beam, and the at the hinge at the c point, and we have a spring at the point b, and that spring is attached by the end of like the b, and there is a point a. And if we give like some displacement to point a, and there is some displacement at point b, like where, like if you first you read the question, what is the question asking? Like the rigid beam bc in the fig is hinged at the c and excited by the force in the spring ab, and where the motion of A is specified the zt. Now first we have to determine the equation of motion of the beam in terms of the vertical displacement vt at the point B. Okay, like we have to first determine the equation in terms of the vt, and then the another we have to equation of motion in terms of the force F1 in the spring AB. So like second part, let us forget this for this time. First focus on the first part, like the we have to determine the equation of motion in terms of the vt. So like if we give a like there is a displacement vt, like forget about this part, we will discuss it later. Like if we have a beam, there is a spring here k2, and there is a damper here c, and there is a hinge at this point. If there is a vt displacement, so that will be deflected like this. So there is a theta here. So what is the displacement in this K2 spring? That will be the L by 2 into theta, and displacement in damper also, like the velocity of in the damper also, L by 2 into theta dash. So let the rigid beam rotate by theta, which we have shown in this figure, and displaced by the Vt. So the free body diagram you can see also, like there is a Vt displacement at the end of this, and there is a theta is the rotation of the beam, and then L by 2 theta is this displacement in this spring, and L by 2 theta dot is the force in the damping. So now we have to develop the free body diagram of this equation. Okay, so due to the like the this is the beam, and that is rotate, so resisting force will be like that will be applied in the opposite direction. This is the spring force fs2 ft, and there is the inertial force of the rod, and there is some force in the spring, like because there is a beam and this is a spring, and there is excitation in this. We have applied the excitation here zt, and there is a vt is the displacement at that point, and that is the K1 is the stiffness. So there is also the force developed in this spring. So what is the force developed in this spring? Let us, that force is the Fs1. Okay. So now take the moment about the hinge. Okay. If you take the, like this is the L by 2, this is the L by 2. If you take the moment about the hinges or the point C, you will get the Fs into L1 minus Fs2 into L by 2 minus Ft into L by 2 minus I theta dot is equal to 0. So now first calculate the inertial mass inertia of the rod. Anyone can tell me what is the inertial mass of this rod? Like as we have discussed, if the bar is the length L and the about the midpoint, the inertial is the ml square by 12. So about the end, can anyone tell me like what is the inertial mass about this point? Anyone?
ml square,
No.
ml square by 2.
No, that would be the like if you can calculate like go through this like the parallel axis theorem, that will be the like I naught moment inertia about the center
Oh,
plus mass into what is the distance of this. This is the L by 2. So that would be the L by 2 square. So that will be 1 by 12 plus 1 by 4. If you take it the it is 12, that will be 1, that will be the 3. So that would become 1 by 3. So that become the ml square by 3. Understood?
yes, sir. Yes, sir.
And what is the fs1 like fs2 and ft? Fs2 is simple, like if the displacement is like the rotation is theta, so that is the L by 2 into theta, and you can calculate the theta value is this. What is the theta value? Theta value is the theta divided by, like we have considered the displacement at the point, this is the vt, and the overall length is the L. So theta is the Vt by L. So you can calculate the displacement in the fs2 and the ft1. Now the question is the like what is the displacement fs1? So fs1, like if I have a spring here, zt is there, here vt is there. So when the f, like the force is developed in the spring, if my zt is greater than the vt, sorry, like yes, my zt, if my zt is greater than vt, then the force will be developed in this spring. If my zt is like some like z is equal to vt or less than, then the force is not developed that much in this spring. Okay, so if the here like if the force fs1 will be developed if the zt is greater than the vt, so fs1 will be the k1 into zt minus vt. And same like I we have calculated as a ml square by 3, and the fs2 is the k2 into v2 by 2, because there is the displacement is vt. So if the end of the beam is the displacement Vt, so directly it is a linear relation. So that will be the Vt by 2. So the Fs2 is the K2 into Vt by 2, and Ft is the C into dot by 2. And for the I theta, theta dot is the V double dot T by L. So if we put this value in this equation, like in the these values are put in this equation, you will get the this equation. Now you can rearrange the terms. After rearranging the terms, we get the final equation in terms of Vt. This is my the answer of the part A. Anyone has any doubt in this question?
Excuse me.
Yes.
What if this Zt happens to be less than Vt? The direction of Fs1 has to be reversed in that case, right?
What?
If the value of Zt
Yes.
happens to be less than the value of Vt,
Yes.
then the direction of Fs1
That
will
would be
be
negative.
reversed.
That would be negative side.
Okay, so that modification will be there in the last equation.
Yeah, like you can do like that depends on your like in this we assumption that the jet is greater than vd, like that is the jet is the external force we apply. So due
Okay,
to jet the vt is developed.
right, right, right. Okay, thank you.
Like we give the excitation at the point of the b ab, so due to that the vt is developed, so then we have calculated this in terms of the fs. Anyone has any
Okay.
doubt in this question? You can take your time. If you have doubt in this question, you can ask, or in the previous question as well. If anyone has any doubt, you can ask, because we have one
I
part. Yes.
and the I is always to be considered at the center of the beam.
No, no, we have calculated the I about the at the end of the beam. Like center of the beam, we know the value. What is the center of the beam? Like
Okay,
we always know. Like this is a like the simplest way we can, which we things we remember. Like about the center, any section, what is the value of the moment of inertia or mass moment of inertia? So ml square by 12 we know. If we know the value about the center, then we can directly calculate what is the value of this point at the end, or any other points like this point, this point, this
okay,
point.
okay,
You can
okay.
calculate. So now we are moving to the second part, in which we have to, like this is the same equation, that is the not much difference in the second part. The difference is we have to represent that equation in terms of the f1. F1 like fs1 in terms of the fs1, we are taking it as a f1 in terms of the f1. So you can directly do the things like you can calculate the like your equation in terms of the vt. So you can directly write it as a f1 is equal to k1 into z minus v. So if we calculate f1 is equal to k1 into z minus k1 into v. So k1 is equal to into v is equal to k1 into z minus f1. So my v would be become as a z minus f1 by k1. Now you put the value of v like in all of these like vt, v double dot t, vt, v dot t and vt, and you can find the equation of motion in terms of the f1. Give it try by yourself. Have you understood like what I have done here? Like just rearranging the terms, like just rearranging these terms. Anyone has any doubt or should I move further? Anyone? Anyone? Am I audible or not?
Yes, you're audible.
Yes.
Okay, so because sometime I was thinking my network is fluctuating. So if you are not answering that, I am thinking like I like my network is lost or something else. So like what calculation I have done in the I have written by pen. You can visualize here. Like I have written this is in the PowerPoint also. Like I have rearranged the terms like what I have done previously. This term like this is f1 is nothing, that is the fs1. Okay, so now put the equation like we have the like the previous equation. This in this equation we have to put that value of v and let check what will come out to be this. We put the vt like for the v double dot t we have taken this as like double differentiated, and for the v dot t differentiated one time, and then for the vt this is the given here, and then rearrange the terms again. So this is why the equation in term of the f1. So this is like the second part is only the rearranging the terms, nothing else. Anyone has any doubt in all six question, or you have any other doubt except other is the, like these question outside doubt related to week one only, or you have some problem in the solving the week one assignment, any doubt like any concept problem?
Sir, when there is pulley in the system, there was one question in the assignment
Yes.
for finding the degree of freedom.
Yes,
Can you just throw some light into some problem like that?
like if you like some like the if pulley is here, like that depend also like if like there is a spring here, some mass block is here, like how can I find the degree of freedom of this, the degree of freedom of this system? Can you tell me like what is the degree of freedom system? This is the simplest problem. Like can you tell me the what is the degree of freedom system? This is a pulley.
One,
One. Why? Because the displacement in this spring and displacement rotation of this pulley theta, which are interrelated, like that can be represented in terms of the theta or in terms of the displacement like the deflection of this spring. So same way you can calculate
sir,
the
if that That pulley is mounted on another larger pulley, and the mass is on the larger pulley also. It is the same way.
What is like if we have? Can you tell me again?
That pulley is mounted on a larger pulley.
Okay, like you are saying that there's pulley and that is pulley.
Ah, yes. So the spring is connected to one pulley, and the mass is connected to another pulley.
Like this one and this one. So that
Ah,
is
yes, sir.
also the simple. Like if you have the theta, like theta of the both the pulley is same, na?
Okay.
Like if you have displacement x, like let us support this pulley is rotated by x, and the radius of this pulley is 2r something, and that is the r, or and the displacement 2x. So that is theta is x by r. So displacement in this block also comes into the
Same.
theta into r. So same, that is also one.
Okay.
Not much differ. Like I know that is the like the simplest problem. In the pulley, that question is the weak one. That is very tougher. Some springs are there. I know that is the very. But if you try and think about simply like taking it by the parts, then you will be able to solve it.
Okay, sir.
Anyone, any doubt in all six questions?
There is a rigid link in the middle that will also move in the same direction.
In which
No,
question?
in between the spring, there is any rigid link is connected.
In this question?
In some other questions, there is one question where the rigid link is connected in between the springs.
Yes.
Rigid
So
link.
yes, sir. So the result link is a transfer. What is the result link? Like that is transfer the displacement at one point to the other. That is the
Okay.
same.
Okay.
Like if there is a between the spring, then it can be different.
Okay.
Any other question? Anyone has any doubt? Or if you have any doubt, like you can reach me, you can mail me, or you can ask through the discussion form. Like I have seen there is no questions are asking through the discussion form in the NPTL. Like okay, so any question or should I like conclude this session here? Anyone?
No, sir.
Okay, thank you very much. Like
Thank
if you have any question, you can ask through the discussion form also. That questions we will like discuss in the next tutorial, which will held in the next Tuesday, and like some concept related question in the upcoming assignment I can discuss, not the whole questions of the assignment, like because that is your grading part. So like this concept I have discussed, that is okay up to this. Okay.
okay, sir.